Hello, my name is Bauer Zhang. This is my submission for Lab 3, Circuits, in the course Physics 2212. The purpose of this lab is to apply Kirchhoff's circuit laws and Ohm's laws in order to predict the behavior of circuits with different resistors, capacitors, as well as different orientations. In order to do so, an online circuit simulator is used to simulate real-world circuits. Here is a brief preview of the results of the lab. The fundamental physics principles used in this lab involve Kirchhoff's circuit laws and Ohm's law to understand how elements, for example, resistors and capacitors in circuits, behave in different orientations, such as series, parallel, and resistor-capacitor circuits, also known as RC circuits. Ultimately, a combination of these laws allows for calculation of time dependence in RC circuits. The systems, surroundings, and initial conditions of the lab are as follows. The system is the circuit, the surroundings is the universe, and the initial conditions and assumptions are that the resistance of the wires is negligible, and the resistance of the ammeter is also negligible. Looking at circuit 1, I first predicted the current across each resistor, which I found to be approximately 0.00204 amps. The actual ammeter reading recorded 0.002 amps. When placed in reverse, the reading became negative. When the ammeter was replaced with the voltmeter continued to read the potential difference across the opening, which is the same as the voltage of the batteries, but the ammeter read 0 because the circuit is open, with no closed path for the current to flow. After using a voltmeter to measure the potential difference across different portions of the circuit, we can see that Kirchhoff's laws are followed, as the total potential difference across the loop is 0. Additionally, using Ohm's law to calculate the resistance of each resistor, we can see that the Ohm's law is true to the resistor's true values. When the ammeter is parallel to the 100 ohm resistor, Kirchhoff's node rule states that the current going into the parallel portion will be split between the resistor and the ammeter. Since the ammeter has a resistance of 0, the total resistance of the parallel portion decreases. According to Ohm's law, if the voltage stays the same and resistance decreases, then current must increase, which is seen in the ammeter's recording. In circuit 2, when charging the capacitor, the light bulb's luminosity decreases and current decreases from a maximum to 0. When discharging the capacitor after removing the battery, the light bulb's luminosity decreases and the current decreases from a maximum to 0. For the time dependence calculations, the circuit is set up with a 9-volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb. Then, using equations provided, I inputted the data into an Excel sheet with appropriately formatted columns in order to graph a voltage versus time plot, where the time dependence variable, RC, is the inverse of the slope of the line. Calculating RC gives us 5.988, and the expected RC is the resistance times the capacitance, which yields 30 ohms times 0.2 farads, which is 6. Possible sources of error. Since the online simulator is an ideal model of the circuit, possible sources of error are minimal, aside from human errors when recording time and potential difference. Additionally, rounding errors could alter results. What if? When using an actual ammeter, it would have some resistance compared to the negligible resistance of an ideal ammeter. This, in turn, would increase the total resistance and decrease the current by Ohm's law. If we use a charged capacitor with no resistor in the circuit, then the capacitor would charge instantly according to our ideal model, as there is not resistance to slow the current. However, in actuality, most components in a circuit have some resistance, including the wires, and will cause less current to flow through the circuit and to charge the capacitor in a non-instant time. And that wraps it up for lab